I'm Vanessa Stewart. Thanks for joining me and my partner Alan Roberts as we bring you part 2 of the Math Made Easy video series on plane geometry.
In the first videotape, we covered basic concepts like points and lines. Today, Vanessa and I will introduce polygons, many-sided figures that are constructed by joining line segments together. Here are some examples.
The angles that are inside of the polygon are called the interior angles. If each interior angle of the polygon is less than 180 degrees, then we say that the polygon is convex. These figures are all convex polygons because all of their interior angles are less than 180 degrees.
On the other hand, this polygon is not convex. Notice that it contains an interior angle that is more than 180 degrees.
Here are some more examples. Decide whether each of the following figures are polygons. And if it is a polygon, decide whether it is convex or non-convex.
This first figure is a triangle, which is a three-sided polygon. It is convex. We'll spend a great deal of time discussing triangles.
This figure is also a convex polygon. A four-sided polygon is called a quadrilateral.
What about this figure? This is not a polygon at all. One of its boundaries is not a straight line segment.
This is not a polygon either. A polygon must enclose an area. This figure has a gap.
What about this figure? No, we do not call this a polygon. This is actually two triangles, so we have two polygons, not one.
This figure is a five-sided polygon. A five-sided polygon is called a pentagon, and this pentagon is a convex polygon since all of its angles measure less than 180 degrees.
You may have heard of the famous government office building in Washington that's called the Pentagon. The reason that it's called the Pentagon is because it has this shape. The building has five sides.
What about this figure? It also has five sides, and it is a polygon, but this is not convex. Notice that one of the interior angles is more than 180 degrees. In the future, when we say polygon, we generally mean convex polygons.
We usually use capital letters to identify the corner points of a polygon. These corner points have a special name. We call each corner point a vertex of the polygon. Can you identify each vertex in this polygon?
The answer is A, B, C, D, E, and F. Each of these 6 points is a vertex of our polygon. The plural of vertex is vertices, so we can say that this polygon's vertices are A, B, C, D, E, and F.
The sides of the polygon are the line segments AB, BC, CD, DE, EF, and FA, and the interior angles are labeled 1, 2, 3, 4, 5, and 6.
One of the ways that we classify different kinds of polygons is by the number of sides. Notice that we have already described triangles, quadrilaterals, and pentagons. Other names that you may encounter include the hexagon with 6 sides, the octagon with 8 sides, and the decagon with 10 sides. The polygons that we will discuss most in this course are the triangle and the quadrilateral.
Here are a few more definitions about polygons. We say that a polygon is equilateral when all of the sides of the polygon are of equal length. We say that a polygon is equiangular when all of the angles of the polygon have equal measure.
Notice that these two concepts, equilateral and equiangular, are not dependent on each other. Here is an example of an equilateral polygon that is not equiangular. This is a quadrilateral. All of its sides are equal, but the angles are not equal. This figure is called a rhombus.
And here's another quadrilateral. This one has all of its angles equal, and they happen to be right angles, but the sides are not equal. We therefore call this rectangle equiangular, but not equilateral.
A polygon that is both equilateral and equiangular is called a regular polygon. For example, a square is a regular polygon. All of its sides are equal, and all of its angles are equal to each other. All four angles are right angles.
And here are some more examples of regular polygons. In this triangle and in this pentagon, the sides are equal and the angles are equal.
Now we'll examine triangles in much more detail. A triangle is a polygon with just 3 sides. First, let us talk about the names that are given to triangles of various shapes.
We can classify different triangles by the relative sizes of the sides or by the sizes of the angles of the triangle.
First, let us give the names of different triangles according to the lengths of their sides. If all of the sides of a triangle have different lengths, then we call the triangle scalene.
If 2 of the sides are of equal length, then we call the triangle isosceles. Just as we call angles with equal measure congruent angles, we call sides with equal length congruent sides. So we can say that an isosceles triangle is a triangle with 2 congruent sides. The congruent sides are called the legs of the isosceles triangle, and the third side is called the base. The angles that are next to the base and that are opposite the 2 equal sides are called the base angles.
And if all 3 sides are congruent, then we call the triangle equilateral.
In review, these 3 shapes are called scalene, isosceles, and equilateral.
Another way to classify different kinds of triangles is by the measure of the angles. Remember that we call an angle acute if its measure is less than 90 degrees. We call it a right angle if it measures exactly 90 degrees, and we call the angle obtuse if it measures more than 90 degrees.
If all of the triangle's 3 angles are acute, then we call it an acute triangle. If one of the angles is obtuse, then we call it an obtuse triangle. And if one of the angles is a right angle, then we call it a right triangle.
The side that is opposite the right angle is called the hypotenuse, and the other 2 sides are called the legs.
Here are some examples. What can you say about this triangle?
This triangle has all of its sides equal, which makes it equilateral, and the angles are all acute, so the triangle is acute.
What about this triangle?
Well, one of its angles is a right angle, which makes it a right triangle. And since 2 of the sides are equal, the triangle is isosceles. These are its legs, and here is the hypotenuse.
Here's one more example. What can you say about this triangle?
Well, all of the sides are of different lengths, so the triangle is scalene. And since there is an obtuse angle, this is also classified as an obtuse triangle.
Here's a very interesting and important fact about triangles. The sum of the measures of the 3 angles of any triangle is exactly 180 degrees.
Let's look at an example. Look at this triangle. We tear off 2 of the angles, and then we place these 2 pieces right next to the third angle of our triangle. Notice that the 3 angles add up to a straight line, which is 180 degrees.
You may want to stop your VCR and try it out yourself. Just take a piece of paper, carefully draw a triangle on it, and cut out the triangle. Then tear off 2 of the angles at the corners and line them up with the remaining angle. You'll see that the 3 angles add up to a straight line.
We could do the same experiment for any triangle, and it will always work.
Does this prove that the sum of the measures of the angles of a triangle is always equal to 180 degrees?
Well, that depends by what you mean by the word prove.
In the study of logic, there are 2 methods that people use to prove things. One method is called induction, and another method is called deduction.
If we try an experiment many times and each time we get the same result, we may become convinced that next time we will probably get the same result. For example, you might turn on a water faucet and notice that water begins to flow. You might do the same thing with a whole lot of water faucets, and each time note that water begins to flow. This process of generalizing from a set of examples is called induction. But this method does not prove the principle for sure. As a matter of fact, you just might try out some water faucet that is out of order, and the experiment will not work.
With triangles, you might perform our experiment for many different shapes of triangles. Cut up and tear up dozens of sheets of paper, and the measures of the angles will always add up to 180 degrees. That leads you to believe that the sum of the measures of the angles of any triangle equals 180 degrees. But this reasoning does not prove it 100%.
The second logical method for proving things to be true is called deduction. In deduction, we start with a set of accepted facts. Then, in a step-by-step fashion, we list statements that necessarily follow from these accepted facts. The first basic facts that we take for granted are called axioms. Here's an example of an axiom that is used in proving that the sum of the measures of the angles of a triangle is 180 degrees. Through a point that is not on a given line, exactly one line may be drawn parallel to the given line.
To show what this axiom means, think of a given line and some other point. Of the lines that can be drawn through that point, exactly one is parallel to the first line.
In geometric deductive proofs, there's a certain discipline that people follow. First, we write down the statement that we are to prove. This statement is referred to as the theorem. We write down the theorem in two parts, what is given and what we want to prove. Then we write the proof in two columns. The first column contains the statements that lead to the proof, and the second column contains the reasons for the statements. These reasons are either axioms or other facts that were previously proven.
Let us state and prove our theorem using this discipline. The theorem that we want to prove is that the sum of the measures of the angles of a triangle is 180 degrees.
What is given and what do we need to prove?
We are given a triangle ABC. We want to prove that the measure of angle 1 plus the measure of angle 2 plus the measure of angle 3 equals 180. Here is the proof. The first statement of the proof is, through point B, draw a line that is parallel to AC. The reason for this step is the axiom that we mentioned before. Through a point that is not on a given line, exactly one line may be drawn parallel to the given line.
The second step of the proof is that the sum of the measures of angles 4, 2, and 5 equals 180 degrees. The reason is, a straight angle contains 180 degrees.
The next step is that the measure of angle 1 equals the measure of angle 4, and also the measure of angle 3 equals the measure of angle 5. The reason for that is because alternate interior angles of parallel lines are congruent, as we discussed in the previous videotape.
Finally, we have that the sum of the measures of angles 1 and 2 and 3 equals 180 degrees. The reason for this final step is substitution. We substitute the measure of angle 1 for the measure of angle 4, and we substitute the measure of angle 3 for the measure of angle 5.
A statement that follows directly from a theorem is called a corollary. Here are some interesting corollaries to the above theorem.
The acute angles of a right triangle are complementary. Remember that two angles that add up to 90 degrees are called complementary. Since the sum of all three angles is 180 degrees, and the right angle uses up 90 of them, we are left with 90 degrees for the remaining two angles.
Here's another corollary. Each angle of an equiangular triangle measures 60 degrees. Since all three add up to 180 degrees, and all three are congruent, each of them measures 180 divided by 3, or 60 degrees.
And another corollary. If two angles of one triangle are congruent to two angles of another triangle, then the remaining angles are congruent. Since the total for each triangle is 180 degrees, and since both triangles use up the same amount for two of the angles, exactly the same amount is left for the remaining angle of each triangle.
Angle 4 in this picture is called an exterior angle of the triangle. The measure of this exterior angle is equal to the sum of the measures of angles 2 and 3. Can you tell why?
Together, angle 1 and angle 4 measure 180 degrees. Also, the measures of angles 1, 2, and 3 total 180 degrees. So, the measure of angle 4 must equal the sum of the measures of angles 2 and 3.
Here's an example for you. To find the answer, you'll also need to use some of the information about parallel lines that was covered in the first tape of this series. In this figure, side BC is parallel to side DE. We're given that the measure of angle BCA is 45 degrees, and the measure of angle BDE is 75 degrees. Find the measure of angle BAC.
If we know the measure of two angles of a triangle, then we can find the measure of the third. We're motivated to find the measure of angle ABC. But angle ABC is congruent to angle ADE. Because these two angles are corresponding angles of parallel lines that are cut by a transversal.
Therefore, the measure of angle ABC is 75 degrees. Since the sum of the measures of all three angles of triangle ABC is 180 degrees, and we know that two of the angles measure 45 and 75 degrees, how many degrees are in the remaining angle?
180 minus 75 minus 45, giving the answer of 60 degrees.
Again, the theorem that we proved and that we've just been discussing is the sum of the measures of the interior angles of a triangle is 180 degrees. We can use this theorem to derive some other conclusions. For example, we can find the sum of the measures of the interior angles of any other polygon.
Let's start with quadrilaterals. What is the sum of the measures of the four interior angles of a quadrilateral?
Any quadrilateral can be broken up into two triangles by drawing a diagonal between two opposite corners. The four interior angles of the quadrilateral are made up of all of the interior angles of the two triangles. The sum of the measures of the interior angles of each of these two triangles is 180 degrees. So in total, the quadrilateral's interior angles contain 180 plus 180 for a total of 360 degrees.
What about a pentagon? How many triangles can we divide a pentagon into?
We pick one corner, let's say corner A. We draw diagonals from A. How many diagonals can we draw?
We can draw a diagonal to each of the opposite corners except for the adjacent corners B and E. In total, we have drawn two diagonals. They break up our pentagon into three triangles.
So we conclude that the sum of the measures of the interior angles of a pentagon equals 3 times 180 for a total of 540 degrees.
In general, suppose that we have a polygon of any number of sides. Let us call that number of sides n. How many diagonals can we draw from some corner A?
We can draw diagonals to all of the other corners except for the two adjacent corners. This breaks the polygon into triangles. How many triangles?
The quadrilateral that had 4 sides was cut into 2 triangles. The pentagon that had 5 sides was cut into 3 triangles. The polygon that has n sides can be cut into n minus 2 triangles. And since each one of those n minus 2 triangles contains 180 degrees, our polygon contains a total of n minus 2 times 180 degrees.
Here's an example for you. What is the sum of the measures of the interior angles of an octagon? Press the pause button while you calculate the number.
An octagon has 8 sides. Rn equals 8. N minus 2 equals 8 minus 2, which equals 6. So an octagon has 6 times 180 degrees for a total of 1,080 degrees.
So far in this videotape, we haven't taken advantage of any of the methods of coordinate geometry. We can gain further insights about triangles by using coordinate geometry. Let's look at a typical triangle that is placed on the coordinate grid.
We'll call the side at the bottom of a triangle the base. We draw a line segment from the opposite vertex perpendicular to the base. This segment is called the altitude. The length of this altitude is called the height of the triangle.
Let's figure out the area of this triangle. That is to say, how many square units fit into the triangle.
In order to find the area of the triangle, let us first consider the rectangle in this picture. How many square boxes are in this rectangle?
There are 24 boxes in the rectangle. We say that the area of the rectangle is 24 square units.
Notice that the rectangle is 3 boxes high and 8 boxes wide. The total area can be obtained by multiplying the height by the width, giving us 3 times 8, which equals 24.
What about the area of the triangle? The area of the triangle is exactly 1/2 of the area of the rectangle. You can see that by looking separately at the left side of the altitude and at the right side of the altitude. On the left side, the rectangle contains 9 square boxes. Half of that area is in the triangle, for a total of 4½ boxes. On the right side, the rectangle contains 15 square boxes. Half of that area is in the triangle, for a total of 7½ boxes. We conclude that the triangle's area is 1/2 of the rectangle's area. Since the rectangle's area is 24, the area of the triangle is half of that, giving us 12.
In general, the area of a rectangle is the length of the base times the height. So for any triangle, the area is 1/2 of that amount, giving us 1/2 of the length of the base times the height.
This is often expressed as a formula. A equals 1/2 of B times H, where A is the area of the triangle, B is the length of the base, and H is the height.
Here are some examples. First, find the area of this triangle. Its base is 10 units and its altitude is 5 units. You may want to pause your VCR and figure out the answer for yourself.
B is 10 and H is 5. Substituting into the formula, we have that the area is 1/2 of 10 times 5, giving us 25 square units.
Here's another example. What is the area of the triangle whose 3 vertices are at coordinate positions 0, 0, 5, 0, and 0, 8?
First, let us draw 3 points on the coordinate axes. 0, 0 is the origin, the point where the x-axis and the y-axis meet. Let's call it O. The point 5, 0 is on the x-axis, 5 units to the right. We call it A. And the point 0, 8 is on the y-axis, 8 units above the origin. We call this point B.
Now we need to find a base and altitude of the triangle and to determine their lengths. If we call OA the base of the triangle, we see that it is 5 units long. Although OB happens also to be one of the sides of the triangle, notice that angle AOB is a right angle, so OB is the altitude, and OB is 8 units long.
Now we can substitute into the formula for the area of a triangle. The area equals 1/2 of B times H, giving us 1/2 of 5 times 8 for a total area of 20 square units.
In all of our examples so far, we have shown the base at the bottom of the triangle. It doesn't need to be. Regardless of the triangle's position, we can choose any side and consider that side to be the base. A line segment that is perpendicular to that base and that meets the opposite vertex is considered to be the altitude, and the formula A equals 1/2 of B times H holds true.
Here's an example. What is the area of the triangle whose vertices are at the points 2, 5, 6, 5, and 6, 2.
First, let us draw the 3 points on the coordinate axes. This is the point 2, 5. Let's call it A. This is the point 6, 5. We'll call it B. And this is the point 6, 2, which we will call C.
Since we can choose any side of the triangle as the base, it's convenient to choose either AB or BC. Their lengths can be found easily.
Let us call AB the base. AB is of length 4. Since AB and BC are perpendicular to each other, BC is an altitude to side AB, and BC is of length 3. So the area of the triangle is 1/2 of 4 times 3, for a value of 6 square units.
In some cases, the altitude may even be outside of the triangle. In an obtuse triangle, we have to extend the base in order to meet the altitude. Still, the formula A equals 1/2 of B times H holds true.
For example, consider the triangle whose vertices are at the points 0, 0, 1, 6, and 11, 6. To find the area, let's consider the top side of the triangle as the base. How long is the base? The base is the distance between 1, 6 and 11, 6. That distance is 10.
In order to find the altitude, extend the base to the left. The altitude is the line segment from the point 0, 6 down to 0, 0. This altitude is 6 units long.
So the area of the triangle is 1/2 times 10 times 6. The final answer is 30 square units.
You have seen that the altitudes are useful line segments. They help us find a triangle's area. We now want to mention another special line segment that is associated with triangles. A median is a line segment that is drawn from any vertex of a triangle to the midpoint of the opposite side. Every triangle has 3 medians, one from each vertex.
For example, in triangle ABC that we talked about before, the 3 medians are the median from vertex A to the midpoint of BC, the median from vertex B to the midpoint of AC, and the median from vertex C to the midpoint of AB.
Do you remember how to find the coordinates of those midpoints? We learned that you take the average of the coordinates of the 2 endpoints. A and B both have the same y coordinate of 5. The average of their x coordinates is 2 plus 6 divided by 2, which is 4. So the midpoint of AB is at 4, 5.
B and C have the same x coordinate of 6. The average of their y coordinates is 5 plus 2 divided by 2, which is 3.5. So the midpoint of BC is at the point 6, 3.5.
The x-coordinate of the midpoint of AC is 2 plus 6 divided by 2, which is 4. The y-coordinate is 5 plus 2 divided by 2, which is 3.5. So the midpoint of AC is at 4, 3.5.
This concludes the second videotape in the Math Made Easy Plane Geometry series. We've learned about various polygons and especially about the 3-sided polygon or triangle. We spent some time on logical proofs as they are used in geometry. Finally, we use the methods of coordinate geometry to learn more about triangles.
Rewind and review this tape as often as necessary until you've mastered the material. Then join us next time for an in-depth study of triangles. Until then, we're your hosts, Alan Roberts
and Vanessa Stewart. Thanks for working along with us. We'll see you again soon.